In this video, we'll cover methods for comparing two means. The slides come from a short course in the School of Social and Community Medicine, and they originate from Chapter 7 of Kirkwood and Stern, Essential Medical Statistics, which is in your reading list. So we'll first of all distinguish between paired and unpaired data. We'll also take a brief look at the t-distribution, and in particular we're interested in when and why it is used instead of the normal distribution, which we've already come across. We'll also cover confidence intervals and hypothesis tests for paired and unpaired data using the normal distribution and the t-distribution. So let's first get a handle on paired and unpaired data using a couple of examples. First of all, we have a randomized controlled trial to study the effect of formula milk with or without long-chain polyunsaturated fatty acids. So that was done in a random sample of newborn infants. And the main outcome measure was blood pressure at 6 years of age. Here's the main table of results. It summarizes the mean outcome by intervention group. And there's a measure of effect, namely the difference in sample means, a confidence interval, and a p-value, which represents a test of whether the groups have the same blood pressure. So here's another example. This time we have a random sample of patients with chronic obstructive pulmonary disease. The sample size is 48, and each patient received a 4-day course in morphine and a 4-day course of placebo or a sham treatment. And the order that they received, that was randomized. And the main outcome measures was dyspnea using a visual analog scale. And here are the results. The outcomes were measured in the morning and the afternoon. So the effect measure this time is the mean difference in dyspnea score, morphine minus control. So a negative number means a reduced dyspnea score in the morphine group versus the control group. The p-value is a test of the null hypothesis that the true mean difference in dyspnea score between treatment with morphine and treatment with placebo is equal to 0, or there's no effect of treatment. So for the first example, we had two groups or two samples of patients measured once. There was no connection between newborns in each group. We could not pair them up in any way and calculate a difference between pairs. It wouldn't make any sense. So we call this an unpaired comparison. For the second example, the dyspnea study, each patient received each treatment. So the difference in effect was calculated for each patient, and then a mean of differences obtained. This is a paired comparison. This is actually called a crossover study or crossover trial, where each individual serves as their own control. Other examples of paired data might be a sibling study, where we know one sibling has been exposed to something and the other hasn't, and we compare outcomes between siblings. Another example might be an ophthalmological study where different treatments are given to each eye. So here's another example of paired data. It shows blood pressure data from 10 subjects measured on 2 occasions separated by time. In between blood pressure measurement, these subjects took a course in statistics. To look at whether blood pressure changed, we're interested in the sampling distribution of the mean of the paired differences and its standard deviation. So these are the sample statistics we need to do inference. The measure of effect we're interested in is thus the population mean paired difference in blood pressure. Because we use paired differences, this is just like doing inference for a single sample mean, which was explained in an earlier video on central limit theorem in practice. We're just working with the observed differences rather than the actual observed values. If a mean paired difference of 0 is plausible with this sample, then it would suggest that a course in statistics has little influence on blood pressure. So we can plug values from the summary statistics of the differences at time point 1 to time point 2 here, This gives us a standard error of approximately 2.5 for the sampling distribution of the mean paired difference for blood pressure from time 1 to time 2. So remember we said that when sample sizes are small, we use a t-distribution to account for the sampling error in the estimate of the population standard deviation, because we need that population standard deviation to estimate our standard error. So the t-distribution is similar to the normal distribution in that it is symmetrical around the mean, but it has heavier tails, as you will see in a minute. There are lots of t-distributions, not just one, like the normal distribution, and the precise form or shape of the t-distribution is determined by something called the degrees of freedom. This is basically the amount of independent information in the sample and is used to construct the probability distribution. Specifically, the degrees of freedom determine how heavy the tails are, and the degrees of freedom are determined by the sample size minus 1. So a t-distribution becomes more and more similar to the shape of the normal distribution as the sample size increases. And you can see that in this plot here. So as the degrees of freedom or sample size gets bigger, the t-distribution tends towards the normal. It's fairly similar with a sample size of 21 or so. So what effect would that have on the confidence interval and the hypothesis test? Well, the fatter tails mean that t has more of its values distributed away from the null. This means if we use t for a confidence interval or a hypothesis test when the sample size is small, as we should do, then our confidence intervals will be wider and our hypothesis test more conservative. By conservative, I mean it'll be harder to observe a lower p-value. And this makes sense when you consider that we are taking into account the extra uncertainty of our estimate of the population standard deviation that we use to estimate the standard error of the sampling distribution. So we'd say that we're getting a more conservative estimate of the confidence interval and of the p-value. So let's use our example of blood pressure to compare 95% confidence intervals using a normal distribution with the t-distribution that is the more correct one for smaller samples. So the general form of the confidence interval is here. As we've seen, this part, the confidence coefficient, is 1.96 if we're using the Z or normal distribution. It's a Z statistic that contains the middle 95% of Z values in our probability distribution. This changes if we're using the t-distribution because the tails are heavier, so the sampling distribution is wider or has more variability. And you can see for a t-distribution with 9 degrees of freedom, the t-statistic that captures 95% of t-values is 2.26. So it makes the confidence interval wider. And you can see that in our example, we get confidence limits of 4.3 to 14.1 using the Z distribution, and confidence limits of 3.54 and 14.85 using the t distribution. But both suggest that learning statistics is bad for your blood pressure. It's just that there's a wider range of plausible values for the population mean difference when we use the more correct t distribution that accounts for this uncertainty in estimating the population standard deviation. So what about hypothesis tests using the t distribution for paired data? Well, we call this a paired t-test. It's done using the same sequence of steps and principles as we've described. So we start with the null hypothesis. In this case, learning statistics is not associated with blood pressure. And then we use our data to look for evidence against this null hypothesis. And we calculate the test statistic in exactly the same way as for a Z test. It's the point estimate divided by the standard error. So here we have a value of 3.68. Now the key difference between using a normal distribution and a t distribution is that we now use the t distribution to calculate the p-value rather than the Z distribution. And we can see that the probability of obtaining a t-statistic lower than minus 3.68 is 0.0025, which is half of our p-value for a two-sided test. So the p-value is this value multiplied by 2, which is equal to 0.005, and that's just written here. So you can see that the p-value from the t-distribution is quite a bit bigger than the p-value from the normal distribution, which is 0.0002. This is what we would expect. Nonetheless, both are very small, and the p-value from the t-test is interpreted in exactly the same way as we've described for p-values generally. So here's one interpretation. So there are 5 chances in 1,000 that a difference in means of at least the observed magnitude could have arisen if the null hypothesis was true. So this is a very small probability and is strong evidence against the null hypothesis. So we've described inference for small samples involving paired data. What about unpaired data? In this case, we're comparing 2 sample means. So here we have data on forced vital capacity from 20 none or never smokers, and we can think of that as one random sample, and from 20 people who have smoked, so we can think of that as another random sample. So the sample mean is 4.05 in the never smokers and 3.95 in the have smokers. We could informally compare the 95% confidence interval in each of the 2 samples. So here's the result in each of those samples. So there's lots of overlap in these 2 confidence intervals, which is indicating that there's a large range of plausible values in each group that are compatible with these groups having the same forced vital capacity, or FVC. Or put another way, there's unlikely to be strong evidence against the null hypothesis that the groups have the same underlying FVC. However, we ideally want to directly compare these 2 groups in some way, rather than just describe each. So what I mean by this is that we want a measure of effect, a single statistic that describes the difference in forced vital capacity between these 2 groups. As we saw at the beginning of the video, this can be quantified by just taking the difference in the 2 sample means. And of course, we recognise that this is just a single point estimate, and it would vary if we took another sample and another sample and another sample. So we need to work out the standard error of this point estimate, the difference in means. So the standard error of the difference in means is what we need to estimate. And that's given here by this formula. So it's equal to the square root of the sum of the squared standard error of the mean in each sample. And it's written more fully here. It's not necessary to remember these formulas for the standard errors. They're something that can be looked up or just simply ignored if we use a computer. They're only really relevant to statisticians who need to know how they're derived. So to calculate a confidence interval, we use the standard formula for a confidence interval that you should be pretty familiar by now with, and should be able to see the connection of this formula with many of the approaches that we're discussing. So if we're using the Z or normal distribution, and we would use that if the sample is big enough, then our confidence coefficient is 1.96 as per normal. Another number that you should be well familiar with. And if we're using T, which we probably should use in this case, because the sample size is not greatly massive, it was 40, then we use the T distribution with 38 degrees of freedom. And we use 38 because the degrees of freedom for a 2 sample test is determined by the total sample size minus 2. And why do we take 2 away from the degrees of freedom? Well, you can think of the means in each of the 2 samples as being fixed. So that information is not free. And so then you have n minus 2, which equals 38 pieces of free independent information. And it's not necessary to know this, but you will probably get a feel for it when you look at other distributions such as a chi-squared and F distribution that also depend on this notion of degrees of freedom. In this case, the 95% confidence coefficient for a T distribution with 38 degrees of freedom is 2.024. So the hypothesis test of two sample means follows exactly that as shown before for one sample test and paired tests. We calculate a test statistic and compare it to the normal or the T distribution, whichever is appropriate. And the null hypothesis is written as the population mean in one sample is equal to the population mean in the other sample. mu1 equals mu2. So with our smoking example, the mean forced vital capacity in the population of never smokers is equal to the mean forced vital capacity in the population of people who have smoked. And whenever we do any inference, there are assumptions, and they come from the fact that we're assuming that the sampling distribution or probability distribution follows some theoretical properties, because the probability distribution is theoretical in nature. If they don't follow these properties, then our inference may be invalid and we may come to the wrong conclusions. Most of the tests we describe are fairly robust to quite strong violation of these assumptions, but it's important to be aware of these assumptions when doing any analyses. So we've seen with other inferential methods we've looked at so far, so the one sample confidence intervals and tests and paired confidence intervals and tests, that we assume the observational units are independent. And if we use a normal approximation via central limit theorem, then we also have conditions concerning the sample size to satisfy in order for it to be valid. With a two-sample test, there is an additional assumption, and that is that the standard deviations in each sample are approximately equal. And we can adjust the degrees of freedom of the T distribution if this is not met. So this is an extra assumption with the two-sample t-test. So that's it. The main things that have been introduced in this video are this idea of unpaired and paired data, and also the use of a t-distribution and how it differs from the normal distribution and when and why it is used. So those are the important aspects, and by now hopefully you can see that there's a basic form and a basic structure and a basic logic for all hypothesis tests and all confidence intervals. So there's a lot of repetition involved when we just discuss different scenarios. They all fall around this basic structure.